All right, we'll give it another minute or so as more participants come into the room.
Right.
All right, we'll go ahead and get started. Let me make sure I'm recording. Oh, it is recording. All right, perfect. So I am Anthony Winston, owner of Winston Engineering, and today we're going to be discussing cogeneration for indoor cultivation. And what really spurred this is because quite a few of our cannabis clients come to us without adequate power, or they just they don't have power in the area at all, and it could take up to a year or more for the utility to bring in that type of power. So I've had meetings with Kinsley here, and their cogeneration product is definitely a good solution, especially like in California where you have the automatic power shutoff. If the winds blow too hard, the utility is going to shut your power down because of the whole PG&E and wildfires. They don't want to have that happen again. You're having much more weather events, especially in the Midwest with tornadoes. To the next slide. Excuse me, this is there we go. Just a quick background on Winston Engineering. We provide HVAC, electrical, plumbing, civil engineering, and fire protection engineering for the cannabis industry. So whether that's indoor cultivation, extraction, manufacturing, retail, distribution, it really doesn't matter. We provide those engineering construction permit plans. As you can see from the map, we have worked in multiple states. We consider ourselves a nationwide company because we hold licenses in 11 states, including Nova Scotia, Canada. It's fairly easy for us to get our license in places that we aren't licensed. And next, I will let Brent and Stephen from Kinsley take over. Brent is the director, and Stephen Matthews is over new business development. So, gentlemen, I will let you take it from here.
Fantastic. Can I go ahead and share my screen?
Yes, I just stopped sharing.
All right, awesome. Let's see this. Screen 2. All right, can you see my PowerPoint?
It is loading.
Loading. Just let me know whenever everything comes up.
There we
go. Go ahead. Is it up?
It is.
Nice. Fantastic. So thanks a lot for having us, Anthony. We've been looking forward to this presentation and this webinar to discuss how cogeneration can help cannabis cultivators. As you said, my name is Stephen Matthews. I'm a sales engineer. I'm responsible for new business development for the KES team, Kinsley Energy Systems. And I'm joined here today with the director of our team and our fearless leader, Brent Belker. He will be discussing several of the more technical aspects of our presentation, midway through, and I will come in at the end to finish it off. Let's see if I can get this to cycle. Nice. All right. So first and foremost, the Kinsley Group. The Kinsley Group has been operating out of the Northeast for over 55 years, coming up on 60. Our main business at the Kinsley Group is acting as the Kohler standby gas generator distributor for the Northeast. We have expanded over the last few years to be covering Connecticut, Massachusetts, New York, New Jersey, and even Eastern PA. And from that business, the Kinsley Energy Systems team was born. Kinsley Energy Systems is the Kinsley Group effort to focus on sustainable power generation and distributed energy. We are a value-added CHP equipment and service provider. The Kinsley Group formed a partnership with the Tedem Group. Tedem Group is a manufacturer based out of the Czech Republic who has been in the CHP business for over 30 years. They've installed over 8,000 systems globally and have been expanding into the U.S. with our team, developing some great projects that we will discuss later in the webinar. Our team's main business focus is on supplying high quality, efficient CHP systems. We'll go into a little bit more of the technical details of what a combined heat and power CHP system is. But our business is focused around supplying that equipment and then servicing that equipment for the lifetime of that system. But in addition to that, we provide services that really help bring a full CHP project together. Our team is entirely made up of engineers focused on everything that we can, doing everything we can provide to bring a CHP project together, develop the right solution. So we'll get involved with a customer to understand their energy usage and their power demand. We'll get involved with them to understand how their facility operates and how they use power, how they use thermal energy, how they use hot water and chilled water, and how we can optimize an on-site power generation facility for their application. And then turning that into, the financial analysis, so they really understand the cost benefits of using a CHP system. We do all of this because we know how important switching from the traditional power purchase from a utility and going to a distributed system is, and how crucial it is to get correct. Our team focuses very heavily on providing all services that can be wrapped around that to make sure that the equipment they're purchasing is as optimized for their solution as possible. In addition to that, we support all of the installation and we support the engineering design. Oftentimes we are partnering with, we need to partner with high quality mechanical, electrical, MEP design engineers such as Anthony to really develop this full solution scope as well. And then also partner with great construction services teams to do the site work and installation prep work. But our team will always be sitting there ready to support those services as well and make sure that a CHP system is wrapped around providing the most value to a customer. Now, why are we here today to talk about cannabis? We are a power generation, a distributed power generation equipment provider. Our main focus for the cannabis industry is providing a path towards lower operating costs. We recognize that the existing cannabis market has limited supply, only with no interstate commerce being allowed and the number of licenses being issued are controlled still federally or being controlled by the legislature. We recognize that right now constrained supply is allowing for high prices. But there's an acknowledgement that in the market, as more licenses to cultivate are issued, the supply will inevitably increase. Just like you learned in Economics 101 back in freshman year, as supply increases, prices inevitably fall. This is a tried and true principle of economics, and the only way to maintain margins is to lower operating costs so that you can still be profitable as prices fall. we're here to show an opportunity in energy efficiency and a CHP solution that allow cultivators now to lower their operating cost so that as prices fall, they can maintain margins and continue operations profitably. I'm going to go ahead and pass this off to Brent.
Hey, good afternoon or good morning, everybody, depending on where you're joining from. My name is Brent Belker, and as Anthony and Stephen have said, I am the director of Kinsley Energy Systems. I'll just add something to what Steve said and kind of bring that back around to Anthony's introduction, that in addition to the emphasis on lowering the total cost of your operation, we do recognize that part of that has to do with resiliency and the ability to supply power to your facility. Very often, cultivation facilities are developed in existing buildings to keep capital costs low. These often have limited utility access if it was perhaps a prior warehouse with just a little bit of ventilation and lighting. And so utility upgrades can be expensive. And then there is the potential for unreliable power, especially for facilities like one we'll show you at the end of our presentation we've recently commissioned, that is located at a remove, let's say, from a major city. And so in the attempt to find an area that needed economic development and low cost of land and capital, the facility was located in a place where there's basically no ability to bring high quality utility power to the site. So both of those requirements drive the design of the system, both to ensure that we're reliable, that we have sufficient redundancy and resiliency, whether you're connected to the utility or independent from the grid, as well as reducing your total cost of operation. So here, this chart just shows an example of a cultivation facility that was originally designed with a traditional HVAC system that you would be familiar with: rooftop DX units, differential expansion units that are standard HVAC, but they mostly do what we call sensible cooling. That's lowering the temperature and making things comfortable for you. They're not very good at dehumidification. And so then you often have to add a layer of dehumidifiers in the room, which increases the load still further, both the heat load in the room and the electric load. And so you get this situation where your HVAC load can actually exceed your lighting load and all the other loads in the building. This may be fine for a small facility on the order of a few thousand to maybe 10,000 square feet. But as you scale up, as most of our clients are looking to do, to go from 10,000 square feet to 25 to 50 or 100,000 square feet, this kind of model just doesn't scale. The electric demand is too high. And even if you have utility power, very often the utility will be unable to bring this kind of power to your site in any timely fashion. So upgrades can be expensive and take a long time for the utility to approve and connect. So it's imperative that in addition to your considerations of utility power, that you also try to get that load down as low as you possibly can. And how we do this is a two-step process, really. The first step has to do with centralizing your utilities by using high efficiency air or water cooled electric chillers. And then you have an opportunity in that system to plug cogeneration in. So if you go to the next slide, Steve, the very simple little diagram. We didn't get very technical here at all today. We're happy to go into much more detail with you in the future, but this shows you what a CHP system basically can do. On the right-hand side, we've got traditional utility power, providing electricity, chilled water for cooling and dehumidification, and heat for reheat. Very often, your system will subcool the air in order to dehumidify, and then you need to reheat before the air goes back into the room. On the left-hand side, we've got a combined heat and power system that does all of those functions from a single source. This is the whole point of combined heat and power, is to locate electric power generation on site at the point of use where the waste heat from the generator can be captured and put to use in the facility. So here we use it in two ways. We also provide the heat directly in the form of hot water, just as a boiler would do for reheating. And then any excess thermal demand we put through a device called an absorption chiller, which makes chilled water. So these will be used in air handlers. Then it's called a 4-pipe system, where you send chilled water and hot water to and from each air handler. And you have coils within the air handler to first dehumidify, cool and dehumidify, and then return the air back and temper it, whether it needs to be further cooled or heated. Very often these air handlers will also include a heat exchanger within that can actually take advantage of the heat coming out of the room from the lights and use that to preheat the returning air back to the room. So it makes a kind of a figure 8 sort of a path through the heat exchanger in both directions, so that air coming out of the dehumidification cycle pre-cools the air coming into it. The air coming into the dehumidification cycle preheats the air returning to the room. In this way, we're really optimizing the total system efficiency and actually minimizing the size of the CHP that you need, both in terms of thermal and electric power. And that's really the key. We don't want to oversize or overprice a CHP system. We want it to be exactly right sized for maximum efficiency. So if you go to the next slide, this shows an example of a same facility, about 75,000 square feet of canopy. It started off as a 6 megawatt load. And after adding central utility, high efficiency chillers, energy recovery, air handlers, and CHP, it becomes more like a 3,200 to 3,500 kilowatt facility. So reducing your total power demand almost in half. At that point, you may have a cooperative utility who can provide that much power and still want to interconnect your CHP system so that you've got a redundant system where the CHP is backed up by the utility. When the utility loses power, the CHP automatically shifts into emergency mode. It's called islanding, and it begins to operate the facility independently without interruption of power. When the utility comes back, the CHP switches back, the main utility breaker closes, and the CHP switches to parallel and cooperate again with the utility. So in this way, we've got the best of all worlds. We've got the high efficiency of CHP and the resiliency of a backup power system, as well as utility power to handle transients. So with that, I'll pass it over to Steve, and he'll take it from here.
Great. Thank you, Brent. Hey, so we did just cover a good bit of technical information. And while that information is fresh in your heads, I will open this up to any questions, whether you'd like to unmute your mic and go ahead and ask, or if you want to drop it into the chat box.
I think we have a Q&A box down there, but I had a question. I saw on the diagram about the CO2 production how does that particular system work? Something tells me you're not just flooding the room with CO2 and it's in some kind of controlled state. Can you explain that controlled state? And also, are you able to somehow store it for later use if you wanted to?
Thank you for that question, Anthony. It's a good one. So far in closed cultivation spaces, CO2 recovery hasn't been used that much. It's much more common in a greenhouse application, where in fact you do allow the cleaned exhaust from the CHP to flow through the ventilated greenhouse and maintain somewhere around 1,000 or so parts per million CO2. It is possible to do CO2 recovery for closed cultivation, but it does require a fairly complicated control system and a very well laid out facility that ensures the flow of the CO2, to the rooms with a minimum head loss and a minimum of complication of ducting and control. So usually CO2 recovery is most economical in states like California, Massachusetts, New Jersey, where the requirements for emissions are so stringent that you have to use what's called selective catalytic reduction, which really is the first step toward cleaning up the CO2 exhaust. Then it just needs to be cooled and then provided to the facility. In states that don't require selective catalytic reduction, more rural states, for example, the cost of adding SCR is usually prohibitive. So it's really a balance between the cost and the complexity of supplying CO2 into the facility.
Are you then able to store it? I guess maybe I missed that part. Can you capture and store it?
Yes, you can compress and store CO2. Again, that's a question of economics, whether it pencils well compared to traditional CO2 systems.
I see we have actually one of our clients, Thomas Lopez, on, and he had we spoke about this webinar a few days ago, and I forgot what his question was. So hopefully he puts it in the Q&A. But one question that I did have, obviously this comes down to penciling out in terms of finances. Where do you guys see your units kind of apples to apples, let's say a 1 megawatt CHP system versus a 1 megawatt generator, or because your system is so much more efficient, you're able to get a smaller CHP unit?
Yes. So generally, the CHP units will be designed for 24/7 operation. And so they're more durable, they're higher efficiency, so they consume less fuel and require less service compared to kind of a more standard sort of typical standby generator running in what we call prime power mode. So there's a little bit more capital cost up front for combined heat and power, but it's recovered by the higher efficiency and the lower cost of service. So this is what we call the spark spread, where you stack those three elements of operation. And Steve will talk about this a bit more in a second, but it's the cost of capital, the cost of fuel, plus the cost of service is your total cost of generating a kilowatt hour from the CHP. And you compare that to the cost of utility power. And when you have a delta there, then you've got what's called a spark spread that pays you back, pays for the CHP system.
In terms of timing it, so there's opportunity for clients to save money during peak demand when the utility charges a premium. Are you able to time your unit to come on at certain times of the day so that you're essentially off the grid? I know you mentioned islanding, but that seemed like more in an emergency case, but are you able to do it just to save you money on the utility if you're connected to the grid?
Yes, you can. And so the CHP can be sort of dispatched to carry any amount of load. But generally with CHP, what you want to do is run it as much as possible to get the most value out of that high quality, durable engine that you can. So CHP typically lowers your peak demand across the board. When coupled with the utility, you'll usually control to a what we call minimum utility import and just keep that utility power low all the time. There are applications that are have high peak demands and low periods of much lower demand, where you could use any generator that's qualified from an emission standpoint to do peak shaving as you're describing, because very often the utility will charge you in two ways, right? For demand for that high peak and for the number of kilowatt hours you consume. So when you hit a very high peak, you'll pay for that because they have to provide all the copper and all of the distribution and transmission necessary to deliver that power to you, even if you only demand it for 15 minutes out of the day. So they'll charge you for demand, and then they'll also charge you an energy charge for the kilowatt hours. What you want to do is to level your load as much as you possibly can by alternating flowering rooms and staggering veg rooms, and maintaining as level load as you possibly can for both utility power and CHP. Again, the lower your demand, the more even it is, the better you can size your CHP to run at a nice base load, full load all the time, and get the maximum value out of the engine. In the same way with utility power, the lower and more level, the less copper and other equipment they have to provide to deliver that power to you. So the principles are the same either way.
Absolutely.
I like how you mentioned staggering, because I think that goes into operations as well. I know I'm kind of going on a tangent, but being able to stagger a room allows you to have your employees not have to worry about two rooms and maybe just one, while the other one is still humming along. The other question I had, is there a facility size, I guess, minimum or canopy size minimum that works the best with your system?
Yes.
You're a great straight man, Steve. Take it away.
Yes, good lead in, Anthony. Yeah, so it's we're gonna moving through the presentation. I will get to answering that question just on the next slide. But first off, we want to talk about the benefits that a cultivator can expect when moving forward with the CHP and centralized plant, right? So right at a high level, there's a focus on the cost, the quality control, and resiliency benefit of moving with using a CHP and central plant design in cannabis. Brent already discussed a little bit on the cost side, explaining what in our industry we refer to as a spark spread. The difference in the cost of a kilowatt hour generated by CHP versus the cost of a kilowatt hour generated by the utility. When we're talking about the cost of a kilowatt hour generated by CHP, we're considering capital, we're considering maintenance, and we're considering the cost of natural gas fuel. Now, when I say natural gas fuel, that also presents other options for different fuels, such as renewable natural gas, biogas, even propane. We'll actually discuss a variation of natural gas that Brent was able to use on a project that we just commissioned this spring in a few slides as well. Back to cost. The other opportunity for benefit to a cultivator when it comes to the lowering cost is the increased efficiency that that a central HVAC plant is providing to a cultivator. By going to a centralized plant, by scaling up to a commercial industrial processing solution, this HVAC system is going to be significantly more energy efficient. It'll be lowering your power bill. So it'll lower the amount of energy that you are required to provide for your facility to operate. And that in turn will lower your energy expenses. A centralized plant increases your energy efficiency and lowers your energy bill. And lastly, as we've discussed, in the very foundation of the combined heat and power benefit is the opportunity to recover the free thermal energy from your engine genset, and being able to use that as a resource, oftentimes as hot water, or as Brent discussed, as chilled water, or even in certain applications as steam. Being able to use that free recovered heat and as a resource for your facility. These are the cost benefits of a CHP solution and a central energy plant. Now, the other benefit that you can expect to see is increased quality control. A central plant is going to be able to not only be more energy efficient for your facility, but it'll allow you a higher degree of control of your indoor climate. The central energy plant is a closed loop system consisting of 4 piped hot water and chill water that is feeding and that is powering the air handlers, the dehumidification units, and the energy recovery air handlers that Brent was mentioning. By using this centralized system, you'll have greater control over that indoor air quality, so the temperature and the humidity level. That's going to allow you to increase your quality control. A centralized system allows that because you're going to have more robust HVAC infrastructure as opposed to a distributed traditional, DX mini split units spread out on top of the roof. And lastly is the resiliency benefit. We discussed islanding from the utility a little bit, and that there really is a strong value proposition there for a cannabis cultivator. We understand that every hour a cultivator is down without power, every hour a cannabis plant does not have optimal temperature or humidity levels, or is not receiving grow lighting, there is a significant risk associated as that time period extends. If a utility power plant or distribution or substation is down, then a cultivator can be face the risk of losing entire crops. By utilizing CHP and a distributed power generation source, you aren't facing those risks. You're going to be able to continually supply your facility with the power it needs to maintain the optimal indoor climate, optimal lighting schedules, so that your grow schedule can continue to make product, and your risk of losing product because of outages decreases significantly by producing your own power on site. Now, Anthony, to your question before, what is an optimal size? There are several criteria that we use to consider what is an optimal facility to consider CHP. We really do focus first and foremost on the facility size. Then we start to consider it's the utility, the operating procedures, and then the credit. So as far as the facility size goes, there is economies of scale for a cultivator that's looking to move forward with CHP. As the facility gets larger and a CHP system gets larger, the economic benefit of that system, because of improved efficiency, because of engineering design and installation costs that don't scale as fast as that increased size does, you're going to have better economic outcomes. So we do recommend starting with a 20,000 square foot of canopy, 20,000 square feet of canopy facility, right? So this is typically means that at a high level, to start an analysis, we recommend about an 800 kilowatt CHP system for a facility that's looking to grow about 20,000 square feet of canopy. Of course, we can scale to much larger. And sometimes there are opportunities that a smaller facility could benefit from a smaller CHP system. But we typically like to begin our analysis, and we typically make recommendations for cultivators that have facilities that are at least 20,000 square feet of canopy. Anthony, does that get to the heart of the question you're asking?
No, that's perfect. So you minimum 20,000, but you will do smaller based on other considerations.
Yes. So some other considerations we would consider, specifically is the utility is the relationship with the utility, right? There are often times, like Brent said, with the project that we completed just this spring, that the utility is not able to provide the estimated power, whether that be they're not able to provide it on schedule, with the rest of the cultivation facilities built out, but they're not able to provide it at a cost competitive rate for the upgrades that are going to be required to the grid and to the distribution system. Or if the price for power, the price for kilowatt hour is cost prohibitive. We mentioned spark spread. This is an example that a utility customer that is estimating or has seen cost for kilowatt hour of at least 12 cents would likely see a good marginal benefit in spark spread with going with CHP. Depending if their fuel costs are prohibitive, CHP, we always design CHP systems to try to be under that price point for a kilowatt hour of energy. So when it comes to utility considerations, if they cannot deliver the power on the schedule that is required, if it is an expensive market, or as we mentioned before, the reliability, the benefit of reliability with CHP, if a utility, Anthony, like you mentioned, in California, unfortunately, there are many reliability concerns. That would make the case that pursuing a distributed power generation system like CHP could be valuable for a facility that's under 20,000 square feet, but is certainly valuable for a facility that is over that size. In addition to some of the criteria, we have mentioned operating procedures, the ability to integrate a central utility plant. Often facilities that are currently built out already have an HVAC infrastructure of distributed DX systems across the roof, and unless there is a ability or interest in switching to a central energy plant, a central utility plant, then CHP really does not. It has a much larger challenge to provide the economic benefit that really helps a cultivator to use CHP. We really it's important that a cultivator has the ability, is interested and willing to move towards a central utility plant to really maximize the benefit from CHP. And like you and Brent went back and forth, it's also very important that there is a consistent baseload demand for CHP for power, as we oftentimes want to be running these systems 24/7 as they were designed to do, as opposed to a standby generator that is not designed to be running 8,000 hours a year, but under 100. CHP engines and generators are there designed to be running well over 8,000 hours a year. So having a consistent baseload power demand by alternating lighting, grow room lighting, will not only decrease the size of the system that is required, but it's going to also maximize the utility, the utility of that system. And lastly, the ability, there are credit considerations. not just for purchasing the equipment, but for the ability to finance the equipment. CHP systems have been a energy asset that the industry has been, the finance industry has been providing capital for many, many years. There are hundreds of developers around the country, or thousands, that are incentivized and interested in owning and operating CHP systems as a third party owner for someone like a cultivator. This, of course, does require, a certain amount of financial backup and credit history, but the ability to minimize your upfront capital cost with a third-party owner and operator is a major benefit we've seen for CHP end users. Brent, I wasn't sure. It looked like you might have wanted to jump in there, but if not, I'll just keep going.
No, go ahead.
All right. Awesome. So those are the key factors that we consider for cultivators at a high level when considering CHP, if it's right for their facility. So the project that we've been promising to discuss, this is a 3.5 megawatt, cannabis called CHP plant that we commissioned this spring, and just outside of Harrisburg, PA. It's funny. Our lead project engineer, who worked tirelessly on this project over the last 4 months, is sitting next to me in the office for the first time in 2022, just today, because he has worked so diligently on this plant over the last few weeks and months. What we did here is installed 4 different CHP systems from our manufacturer, the Tetum Group. We have 2 1.2 megawatt systems and 2 555 kilowatt systems. We did this in an effort to provide a N+1 redundancy, meaning that if one of these systems were to go down, there is a backup that can provide the capability of complete power to the facility. This is a requirement because this facility is not parallel to the grid. As Brent said, this was a situation where this project was developed in a rural community for economic development, and there was not supply or the ability to supply power for a number of reasons from the local utility to this facility. So they pursued this CHP solution. They were able to stay on their construction timeline. They are now able to begin growing and developing and continuing their business because they developed this CHP and central energy plant solution. Just to move to some of the pictures here, I'm not sure. It's going to be a little bit hard. I wish I had like a pointer, but I do want to point out. So the CHP solutions are what you see here in this top picture. It's clearly these large, beautiful blue. I'm a Penn Stater, so I love navy blue like this. These Tetum packaged CHP systems at the top here. These 2 systems. There's one system in the back that you can't see the package, but this is the stack. These are both of the 1200s, and these 2 smaller systems right here are the 555s. In the bottom picture is what you can see as the central energy plant. That central energy plant contains the chiller, the backup boilers, the hot water pumps, and Brent, am I missing anything in that chiller in the central
chilled water pump? So you can see on the left-hand side, you can see the chilled water piping coming from the building down to the ground, and then it comes toward you in the picture to the cannabis facility. On the right-hand side, you can see the hot water lines coming out. And behind the building, which you can't really see, are cooling towers for dissipating heat from the large water-cooled chillers within the building. So it's a 660-ton chiller, also redundant. So there's 2 chillers within the building, redundant pumps, all powered by redundant CHP.
Right. And that CHP is all powered by a liquid natural gas fueling station that is installed just on the other side of the central energy plant that we definitely cannot see right here. But that LNG station consists of 2 LNG tanks and the gas is decompressed and then supplied directly to the CHP as fuel, and those tanks are refilled every few weeks by truck. So this not only does this plant operate independent of the electric utility, but it also operates independent of the natural gas utility. And as far as we are concerned on this presentation, that is all we prepared. Really would love to have any questions and conversations. Brent and I have plenty of time.
I see that Thomas Lopez. Can you guys see the Q&A? He dropped.
Let's see, Q&A. Yes. Okay. Here was.
So Thomas's question is whether or not the air quality requirements are somehow easier or different for Cogen. Unfortunately, no. It's just a matter, though, of understanding the requirements, providing the equipment that complies, and then building a good relationship with your particular air quality district manager. So they are subject to the same requirements of any power plant or emitting source in the state of California. But so far we've seen they're fairly cooperative when you yourselves are cooperative and plan ahead.
I had a question on the fuel, on the fuel types that your systems can use. Because you mentioned LNG, you mentioned propane. Are you able to utilize diesel?
We do not, for a couple of reasons. For one, it's a very different kind of engine, much higher carbon footprint, and lower efficiency. So all of our units run on natural gas, propane, or liquefied natural gas. We can also run, and we have other installations in other markets, on renewable natural gas or biogas directly from a wastewater treatment plant. Those are some of our favorite projects where we can incorporate renewable fuels into the project. As Steve mentioned, in this case of the site in Harrisburg, we're running on liquefied natural gas, also off pipeline. We've got another project coming up where we'll be operating on compressed natural gas off the pipeline. So any combination, we can find more and more options today for minimizing your fuel costs as well.
Okay. Have you guys, it's probably the last question, but have you guys utilized backup batteries with your systems?
Not
That's
yet.
also a really good question. Becoming very common, and we're looking at a number of opportunities to incorporate energy storage where it can very much complement the transient response of the CHP and provide some short-term power in the event of large changes in load or a shutdown of one unit while redundant units coming online. So we
Okay.
expect to be doing more energy storage in the future.
Okay. So now you get into power quality with reactive and apparent and all those types of loads. Now you're getting into the triangle. So I got you. But thank you guys so much for giving up your time to educate the cannabis community. This will be uploaded on YouTube and shared throughout all of our social media channels: Instagram, LinkedIn, Twitter, hell, TikTok. Maybe we'll see if we can chop it up, but we'll get that out. I'll get the links to you guys. But definitely appreciate your time, and hopefully you get some business from this.
Thank you very much, Anthony, for the opportunity to speak with your clientele.
All right, awesome. Well, you guys have a wonderful day.
Thank you. Have a good one.
All right, bye.
Take care.